Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Okay, okay, very great that I can meet you again in this episode. So today we'll continue our lesson on operating system. So this is the last chapter, and I think this is also the last video I will make to discuss computer science um concepts before we enter into programming realm. Okay, so now we'll discuss the types of operating system. So there are many different dimensions, okay, that marks a characteristic to differentiate various type of operating system. The first dimension that we touch is to specify whether the system is batch or interactive. So in an interactive system that the user program interact directly with the computer, usually through keyboard, display terminal, to request the execution of a job or to perform a transaction. Okay, and they also communicate with the computer during the execution of the job. Whereas for the batch system is the opposite. So the user's program is batched together with programs from other users and submitted by a computer operator. And after the program is completed, the results are printed out for the user. But these systems are kind of rare today. The second dimension specifies whether the system implies multi-programming or not. With multi-programming, the attempt is made to keep the processor as busy as possible by having it work on more than one program at a time, and it actively switch rapidly between them. Okay, whereas for the unit programming, they works only for one program at a time. Then let's see a little about early system. Well, earliest computer, then the program interacted directly with the computer hardware, and there was no OS. Okay, so program in processor code were loaded via the input device, and if an error halted the program, then the error condition was indicated by the light. So the programmer could proceed to examine register and memory to determine the cause of the error. If the program proceeded to completion normally, then the output appeared on a printer. But there are two main problems here. The first one is related to scheduling, okay, and the second one it is related to the setup time. Okay? So this mode of operation could be termed as serial processing. Okay, it means that uh, the user have to access the computer in series. Okay, and then we enter simple batch system. Okay, so early processor were very expensive and therefore it was important to maximize the processor utilization. So the wasted time due to schedule and setup time was unacceptable. Okay, so with such system, okay, simple batch operating system, okay, it also called monitor, the user no longer has the access to the processor, but rather the user submits the job on a card or tapes to a computer operator who batches the jobs together sequentially and places the entire batch on an input device for use by the monitor. Okay, so from the point of view of the monitor will control the sequence of events, and much of the monitor must always be in memory and available for execution. And this is called the resident monitor. While the rest of the monitor consists of utilities and common functions that are loaded as subroutines to the user program at the beginning of any job that requires them. Okay, when the job is completed, it returns control the monitor, which immediately reads the next job, and the result of each job are printed out for delivery to the user. Okay, from the point of view of the processor, at a certain point in time, the processor is executing instruction from the portion of main memory containing the monitor, and this instruction causes the next job to be read into another portion of the main memory. Okay, the processor that execute the instruction, um, okay, in the user's program until it encounters an ending or error condition. Okay, plus the praise of this control is passed to a job simply means that the processor is now fetching and executing progress in the user program. The control is returned to the monitor, means that the processor now fetching and executing instruction from the monitor program. Okay. How about the job setup time? So the monitor will handle this too. For each job, the instruction included in a GCL, job control language. So this is a very specific type of programming language that used to provide instruction to the monitor. Okay. So yeah, this is just detailed explanation to how it operates using Fortran language. I'm not discuss about. Okay, we see that the monitor of TouchOS is simply a computer program and it relies on the ability of the processor to fetch instructions from various portions of memory in order to seize and relinquish control alternatively. And certain other hardware features are also disabled. First, we have to have memory protection. Okay. Second, we have to have a timer to prevent a single job from monopolizing the system. We have a privileged instruction that can be executed only by monitor. We also have interrupts, okay, but early computer model did not have this kind of thing. And if we are given this to OS, then it has more flexibility in relinquishing control and regaining control from user program. But there have been true sacrifices by this approach. So some main memory is now given over to the computer and some processor time is consumed by the monitor. And both of these are forms of overhead. And even with this overhead, the simple batch system have improved the utilization of the computer. The next kind is that multi-program batch system. So yeah, the processor, even for the last example, is always open idle. Okay, so the idle thing is a problem because the I/O devices are slow compared to the processor. Okay, so yeah, you see, unit programming, multi program with two programs, multi program with three programs. So this inefficiency is not necessary because you know that there must be enough memory to hold the OS, the resident monitor one, and one user program. Okay, so we might expand memory to hold 3, 4, even more programs among them, and this is known as the concept of multi-programming or multitasking. This is a central term in discussion of operating system. So as with the simple batch system, the multi-programming batch system must rely on certain computer hardware features, and the most notable additional feature that's useful for multi-program is hardware that supports I/O interrupts and the DMA. So when an interrupt-driven I/O or DMA, the processor can issue an I/O command for one job and proceed with the execution of another job while the I/O is carried out by the device controller. And when the I/O operation is complete, then the processor interrupt and control is passed to interrupt handling process the OS, and the OS will transfer control to another job. Okay. Then we have time sharing system. Okay. For many jobs, it's designed to provide a mode in which the user interact directly with the computer. Okay. So today, the requirement for an interactive computer facility can be met by the use of dedicated microcomputer. And just as multi-programming allows the processor to handle multiple batch jobs at a time, the multi-programming can be used to handle multiple interactive jobs too. And the technique for the layer is called as time sharing because the process time is shared among multiple users. So for this time, multiple users simultaneously access the same system through terminals with the OS, interleaving the execution of each user program in short bursts of quantum of computation. Okay. Next, we'll discuss about scheduling. So the key to do multi-program is actually lays on scheduling. So there are 4 types of scheduling. So first, before we explore the 4 types of scheduling, which are long-term scheduling, medium-term scheduling, short-term scheduling, and I/O schedule, which is shown in the table 8.4. We need to first coin the concept of process. Okay, so yeah, it's somewhat more general than term of job, but the term of process includes that a program is in execution, the animated period of a program is done, and the entity to which a processor is assigned. Now let's just discuss one by one, starting from long-term scheduling. So long-term scheduler, determines which program admitted to the system for processing, and thus it controls the degree of the multi-programming. Okay, so yeah, there are quite some explanation here. Next, medium-term scheduling. So this is part of the swapping function, which typically the swapping indices is based on the need to manage the degree of multi-programming. So the swapping indices will consider the memory of requirement of the swap up process. Next, we discuss short-term scheduling. Okay, while the long-term schedule execute relatively infrequently and make the cross-grain decision of whether or not to take a new process which to take, the short-term scheduler or the dispatcher execute frequently and make the fine-grained decision of which job to execute next. So first we have process states. Okay, so during the lifetime process, its status will change a number of times. Its status at any point is called as state. So state is used because it connotes certain information exists that defines the status of the point. We see the five-state process model that's shown in the figure above. They have new, ready, running, exit, and block, and they can go one to another. So new means that a program is admitted by a high-level schedule, but it's not ready to be executed. Ready means that it's ready to execute and it's awaiting access to the process. Running, it means that the process is being executed by the program, by the processor, I mean. Waiting, it means that the process is suspended for execution, waiting for some system resource. Halt, it means that it has been terminated and will be destroyed by the OS. Okay. For this purpose, okay, to maintain information indicating the state of the process and other necessary information, that we need a process control block in our OS, and they typically contains identifier, state, priority, program counter, memory pointer, and context data. Actually more. Okay, we have also IO status information, accounting information, and actually sometimes more. And when the scheduler set a new job or user request for execution, then it creates a blank process control block and places the associated process in the use. And after the system has properly filled in the process control block, then the process is transferred to the ready state. The next one is scheduling techniques. Okay, so here's the figure so you know how scheduling works. Okay, so the kernel of the OS always resident, and there are a number of active processes, including A and B, each of which is allocated a portion of memory. So, yeah, uh, you see, the problem here is that at later point in time, the process ceases to execute instruction in A and begin executing instruction in OS area, and this is your assignment, little assignment. To understand the three reasons that why this thing happens, I'll show you the context. Okay, let's do this. Okay, it's self-explanatory actually. I'm not going to go there. Okay, so we're discussing about to do its job, then the OS maintains a number of queues. So each queue is simply a waiting list of processes waiting for some resource. So there are some kind of queue. First, we have long-term queue, which is a list of jobs waiting to use the system. We have short-term queue, which consists of all processes the ready state. Okay, and mostly done with round-robin algorithm. And then we have IO queue for each IO device. Okay. So OS manages the IO queues, and when IO operation is completed, then the OS removes the satisfied process from the IO queue and places it in the short-term queue, and it then selects another waiting process and signals for the IO device to satisfy that process request. Now we'll discuss a little about memory management. Actually, this is kind of dedicated discussion, but yeah, I'll make it just short because yeah. So subdivision task class is actually called memory management in OS. So first we have something called swapping. Okay, so uh, you see, the problem is in here. It's true that in this case, memory holds multiple processes and that the process can move to another process when one process is waiting, but the process is so much faster that I/O will be covered for all the processes in the memory to be waiting on I/O, and the processor could be idle most of the time. So what to do? First thing is that main memory could be expanded and so be able to accommodate more processes. But also there are two flaws in the approach. First is that memory is expensive. Second is that appetite of programs for memory has grown as fast as the cost of memory has dropped. So to solve for this kind of problem, we have another solution provided here, which is swapping. Okay, so we have a long-term queue of process requests typically stored on these, and they are brought in one at a time as space becomes available. As the process are completed and they move out in main memory, now the situation is that none of the processor memory are in the ready state. So what to do? Rather than make they remain idle, then the process swaps one of the processes back out to this into an intermediate queue. And this queue of existing processes that have been temporarily kicked out of the memory, and then the OS brings in another memory process from the intermediate queue, or it honors a new process request from the long-term queue, and then execution continues with the newly arrived process. Okay, but sometimes it can make the problem worse, not better, because this I/O is generally the fastest I/O on program, then swapping will usually enhance the performance. Then we have second term, which is partitioning. So yeah, most of the time we have what called a fixed size partitioning. Okay, but although the partitions are need to be fixed size, they don't need to be equal size. Okay? Even with the use of unequal fixed size partition, there will be a wasted memory because sometimes the process will not require exactly as much memory as provided by the partition. So a more efficient process that we use variable size partitions. So when a process is brought into memory, that is allocated exactly as much memory as it requires. Okay, so as time goes on, memory becomes more and more fragmented and memory utilization declines. And one technique to overcome this is that compaction. So for compaction, from time to time, the OS will shift the process in the memory to place all the free memory together in one block to reduce the wasting. So a process in memory consists of instruction plus data, and the instruction will contain addresses for memory location of two types. First is addresses of data items, and second is addresses of instruction used for branching the instruction. But there are two addresses. A logical addresses is expresses location relative to the beginning of the program, whereas a physical address is an actual location in the main memory. Okay, we have starting location, which is called base address to each logical address. Next, we have term of what called as paging. So, yeah, memory is partitioned into equal fixed size chunks that are relatively small, and that each process also divided into small fixed size chunks or subsets. And then the child of the program, known as pages, could be assigned to appropriate chunks of memory known as frames or page frames. Okay. So, yeah, suppose that there are not sufficient unused contiguous frames for a process. Then does this prevent OS from loading a process? The answer is actually no, because we can once again use the concept of logical address. We build a page table for each process, and the page table can show us the frame location for each page of the process. Okay, so the processor must know how to access the page table of current process and present it with a logical address. Then the processor uses the page table to produce a physical address. Main memory is divided into many small equal size frames, and each process is divided into varying size page. The smaller processor requires fewer page and larger processors requires more. Okay, and then I think this is the last one, virtual memory. Yeah. So the first type is demand paging. So uh, demand paging means that each page of process is brought in only when it is needed. That is on demand. Okay. So uh, we can make better use of memory by loading in just a few pages. That is, if the program branches to an instruction on a page not in memory, or if the program reference data on a page not in the memory, that a page fault is triggered. Okay. Yeah, only a few pages of any given process in any time are in memory, and therefore the process can be maintained in memory, and also time is saved. Okay, because we will not do insert out of the memory. But then OS was clever about how it manages this game, and this is called page replacement. And if there's two page that we don't use, and we are doing some trashing. Okay, this is with demand paging, it's not necessary to learn entire process to main memory. This fact has a remarkable consequence that it's possible for a process to be larger than all of the main memory. Because a process executes only in main memory, then memory is referred to as real memory. But a program or user perceives much larger memory, which is then called virtual memory. Okay, then we have page table structure. I think this is not. I will just skip it because it's kind of too specific. Yeah, segmentation. Okay, so this is another way in which addressable memory can be just subdivided, which is called segmentation. So whereas paging is invisible to the programmer and serves the purpose of providing the programmer with a larger address space, the segmentation is usually visible to programmer, and it's usually provided as a convenience for organizing programs, and that is means of associating privilege and protection attributes with instruction and data. So there are a number of advantages here. That it simplifies the handling of growing data structure. It allows program to be all very compatible without requiring entire set of program be relinked and reloaded. Then we also have it lends itself to sharing more processes, and it lends itself through protection. Okay, then this is very specific one related to some processor. Intel. Yeah, we have done actually. Yeah, yippee, we have done the whole book. Okay, actually, I take this book as reference for my videos and some other books actually for the first videos, which is this Computer Organization and Architecture by William Stallings. Okay, so if you want to find the book, you can download there. There are also many kind of new edition. Okay, so this is the book that I use. This is quite a good book. I use it a lot. Okay, yeah, maybe I haven't discussed about kind of parallel processing, multi-core computers, because it's actually type of too specific. But later, if I find that this is needed, then I will back into the discussion. Okay. So yeah, here's a little quote for you today from Deep Roy. So inspiration comes from within yourself. One is to be positive, and when you are positive, good things will happen. And that's all our lesson for today. Thanks for watching, and here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https colon/science.xyz.unux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.